My name is Delian, and today we're going to talk about performance in the wild. Namely, how do you measure and understand what your end users are experiencing as the performance of your app? And throughout this talk, we're going to answer a few questions, but they generally fall into these categories. So the first category is how. How do we measure performance? How do we collect this telemetry? What are the things we should talk and think about when we're collecting this telemetry? We should then speak about why. Why are we collecting telemetry? Why can't we do this in-house? Why do we need to go out there and get this actual real-world data? And lastly, and this is the hardest question of all, we'll talk about why. Why is the app so slow? Or so fast? But so fast never happens. So why is the app so slow? Why are people experiencing such bad performance? And what are the things we should collect and understand in order to alleviate that? So let's start with the how. And hopefully, as we're going through these slides, the why, as in why we're collecting this telemetry, will become a bit clearer. So when collecting data from end-user devices, one of the big things we should think about is the constraints of this problem space. So the first and foremost one is data usage. We cannot afford to collect large payloads of analytics and telemetry. And in general, performance telemetry can take up a lot of data. If you include all the device metadata and all the user session metadata and all the things about your interaction and all the state in the app, that can be an enormous amount of data. And so it's really important that you start designing for as little data usage as possible, as soon as you start. So, for example, do not upload the device metadata with every single performance telemetry sample you get. Upload it once when the user logs in, and then join it on your server backend. And then the other way to sort of alleviate the data usage problem is by randomly sampling. So you could sample in one of two major ways. You either sample by user, so you pick a subset of your user base, and you say that for these people, we want performance telemetry. And this is great because it's really easy to reason about. And for each one of these users, you know what they were doing before and after the interaction in question. And so you have this full view of the app on these devices. However, those users are experiencing your app differently from everyone else. So it's really important to always rotate that subsample of users if you choose to use the sampling strategy, and just keep changing it, maybe every day, maybe every week. So if it's 1%, it's a different 1% every day. The other way to sample is by interaction. So if your interaction happens 1,000,000 times, you can just pick 10,000 of them and then collect the telemetry for only 10,000. So you have this 1 in X sampling rate. And this is easier to implement, but it's a bit harder to think about because you don't know what was happening before and after your interaction, since it's independent from all other interactions on the device. The second effect is the observer effect. So as you're monitoring performance, you're affecting it. You're slowing down the device. The mere fact that you're observing it affects it. And this is generally okay. Like, don't stress too much about this. It's okay as long as the overhead you introduce is not random. As long as the overhead you introduce is not affecting your app in a horrific way, but it is affecting it deterministically. So if you know that, measuring the performance of this interaction slows it down by 3%, you can account for this 3% everywhere. And you can know that the distribution you get out of these samples is the same, just shifted a little bit to the right. Your analytics stack and your upload pipeline need to be really, really fast. They need to allocate very little just to avoid this random overhead of, for example, from garbage collections or other non-deterministic events. And lastly, there just isn't that much telemetry available once your app has been released. You no longer have access to developer tools. You no longer have access to a lot of the OS support. And so there's only so much you can gather from the device in production. But there is enough to have impact, and I hope to show that today. So given these constraints, a natural place to start, and the first thing we did as well, is just collect durations. So this interaction took this long. And you do that for all of your interactions, or the ones you care about. And you do that for a lot of users. The one thing to note here is that it's really important to use the right clock. There are multiple clocks in Linux and on Android as a coincidence. And the system current time millis clock, the clock that we think of as war time, is actually the wrong clock because it can move both forwards and backwards in time. So if the device starts up and your app starts up with the device, you read maybe a timestamp in the 1990s. And then by the end of your interaction, the device will have synced with the tower and will get a timestamp in the 21st century. So your interaction will have an apparent span of many decades. So that's not great. The clock you want is the monotonic clock. It's exposed in Android via two different calls. One is system nanotime, and the other one is system clock uptime millis. They're the same clock, just different units. So using the right clock, and you're getting all of these durations. And if you have 5 users, you're getting 5 numbers back. And so you could stare at these numbers and try to discern why is that interaction taking 10 seconds on this last device, and why is it taking only 104 on the first one? You could stare them individually, but of course that's not of much use. And what you really want is aggregation. And the way I like to explain aggregation is you have a lot of things and you make a few things. So you have a lot of samples and you want to make a few numbers that are meaningful and represent something about these samples that is interesting to you. And I also want to point out that it's useful to think of aggregation as serving 2 separate purposes. There's the purpose of monitoring, whereas we build aggregation that wants to answer the question, is everything okay? Is the performance of my app regressing? Is it okay? And then there's the diagnostics aggregation, which is trying to answer the question, what went wrong? Or what can I improve in this interaction? And those sometimes overlap, and some aggregations are useful for both of these. In fact, most aggregations are useful for both of these purposes, but some of them are useful for only one of these purposes. And I'll start with the simplest aggregation possible. Let's look at averages. And so if you had a college professor like mine, they probably told you to never trust averages for anything ever. And they weren't really wrong. Averages can be really deceitful, and they can basically lie to you. So there is no such thing as an average interaction. But the one useful property of the average is that it's sensitive to every single value. It is not ignoring outliers, and in a way, it's not ignoring slow interactions or really fast ones. And so if you another way to put this is that no user is neglected. No one run of your interaction is neglected in this number. And you may be wondering, okay, so I have this number, what do I do with it? Well, it's great for monitoring, and that's really about it. If this number moves, you know that something in your distribution really changed. It's especially sensitive to large outliers, which in our experience are usually due to bugs. So a common bug in Android instrumentation is that you forget to cancel or stop the marker when you exit the activity. And because the Android lifecycle is so complicated, that happens more often than it should. And so you get these large numbers in your samples. So you get a sample that's maybe hours. And that's a bug, right? And if you were ignoring outliers in the way you calculate your performance metric, you would not see this bug, right? Your interaction would normally last a second. It's now lasting an hour. You're ignoring that. But the average would move. And so the average is actually indicating that, hey, you may have a regression, or maybe you have a bug. Maybe there's something wrong with how you instrumented this. And so we use averages mostly for that purpose, to know is everything okay. And the other thing we do is we cap them at a number that is large enough to be is large enough to be outside of the normal range, but is small enough to not blow up your interaction with decade-long samples and multi-hour samples. So for example, if you get a sample that's 5 hours, we just cap it to 1 minute. And so once you have all of these samples, you should really start to love histograms. That is the best view of the health of your interaction. And usually what you want is something like this. The majority of the users are on the left where things are fast. And then you have this gradual curve to the right. I've removed the axes, but the x-axis span here is 4 times. So the users on the left are experiencing an interaction that is 4 times faster than the one on the right. And so you get a sense to this, and you get a sense for the shape of the interaction as you monitor it over over time. And as you start seeing it shifting, you get a sense of what the bug may be. And so sometimes it starts looking like this. And this is what you don't want. There is something going on with this interaction when there's more than one mode in which it runs. So for the high end of the numbers, so the P90 and above, so the 19th percentile and above, there's something else going on. There's way too many samples there. You would not expect, you want this gradual distribution, and that's what you would normally get. But there's something else going on there, and the sample count just doesn't make sense. And so in order to catch cases like this, it's useful to monitor specific percentiles. The median is great. That is, 50% of your samples are going to be lower than this number. And that is kind of what people think of, what people want when they think of average interaction. It's like the median interaction. But other specific percentiles are also great. So we tend to monitor P90, P75, just to get a sense of, hey, these numbers should look like this, and if something is moving, then maybe we should start digging in. This is exactly what you want telemetry from real devices. There is no way to replicate this distribution in-house. You can at most capture one of these percentiles or one of these numbers, so you could capture the median, and you could probably replicate the median in-house. And I have a device that always is my median device, but I could never capture that P95 or whatever's going on at that P90. And so by having telemetry from real devices, we can identify how our code actually runs, and that there's maybe different modes. So this one was caused by a cache that was cleared every 10th time, which is exactly what you're seeing. Like the P90 is slower because it's clearing the cache. So there's actually two separate interactions. It's the one that had the cache warm and the one that was actually clearing the cache. And in cases like this, it helps to split them into two separate markers. So you're monitoring two distinct code paths. And once you've identified that something's wrong, it's very useful to see who is experiencing this. How are these samples, these slow samples? Is there anything that distinguishes them from the rest of the samples? The very first thing that we like to look at is device year class. Device year class is an abstraction we introduced and open sourced a while back. And it's basically the year in which this device would have been a flagship device. So if you take a really poor low-end device that was built in 2015, and it's a dual-core device, and it has 512 megs of RAM, that device would still show up as device year class 2010. And so even though it was built in 2015, it's actually a 2010 class device. So this interaction is, this abstraction is kind of a really good proxy for device performance. The next one, the next grouping filter that you want to look at is countries. Countries are also an abstraction. So performance doesn't generally tend to vary that much between countries. But a country is an abstraction of the device mix within that market and the network conditions. Network conditions tend to be very distinct between countries. So if your interaction is network bound, country is definitely something that is worth looking at. OS version, of course, Android has gotten better over the years. Splitting by OS version may indicate that you have problems in older versions that you're no longer monitoring. This also correlates very highly with device year class, but not necessarily, because there's some really low-end devices being released with Marshmallow and Lollipop. And lastly, if you have any active A/B tests that you're performing in the application, it's really important to integrate those into your performance telemetry, because you can catch regressions caused by tests much earlier than actually rolling out the test to production. Okay, so what does this all look like in practice? We're going to walk through a regression, an actual regression we had a while back. And so this regression starts off pretty simple. We woke up one day and we saw this. So the regression is there on the left. The red point is when we officially filed it internally as a regression we're tracking. And to give you a sense of timescale, that bump lasted about 4 weeks, I think, 3 or 4 weeks. So it took us a while to narrow down what actually was going on. But then you can see that when we fixed it, we released a new version, and things went back to normal. And that regression was on the order of 10 to 15%, which is a really, really big deal. We generally go after regressions even as small as 1%. OK, so this is an interesting view that I haven't shown before, which is on the y-axis, you get multiple lines. Each one is a separate percentile. So the lowest one is the P10. The highest one is the P90. And this is plotted over time. So how are these percentiles? How is this distribution changing over time? And so the first 3 lines are mostly stable. So that's P10 to P40. And you can see, sorry, to P60. And you can see that the effect shows up, this bump shows up at P70 and above. So 30% of the interactions were basically really slowed down by this regression. But what was fast before is still fast. What was slow became slower. And that was really interesting. So we started digging a little bit more. We then plotted the average per year class, which is what you're seeing here. The top line is year class 2010. The bottom line, the bottommost line is year class 2015. And you can kind of see how, as devices are faster, like they're very distinct lines. And 2015, 2014, 2013, they kind of moved up, but very little. We can totally see the effect in 2010 and 2011. There's something that is making slow devices even slower. But fast devices are still fast. So that kind of explains our percentiles as well. OK, so we have some sense of who's affected. Now what? Well, there's multiple options. First thing we tried, can we reproduce this locally? Unfortunately, we couldn't. It's very rare for performance regression to be reproducible locally, especially ones that were caught only in the high percentiles, where we cannot replicate that point in the distribution locally. Those are really low-end devices that have worn down flash, that have hundreds of apps installed, and it's very hard to get a consistent sample that looks like that. OK, can we look at other things? Maybe there's something those users were doing. Maybe there's something about the OS. Maybe they just updated the OS. By the way, that's a real regression. When someone updated, when a given OEM updated the OS for a specific flagship device, the performance regressed significantly over the next month as the OS was being rolled out. So that happens. But what if nothing comes up? And in this case, of course, nothing came up. Well, when in doubt, there's only one thing to do. Run in circles, scream and shout. At this point, we're basically tearing our we're tearing our hairs out. And the thing we need is more telemetry, right? We need better numbers. We need more numbers. We need more detail. We need something more to basically sink our teeth in. And so there's a class of telemetry that we call resource usage. And these are still numbers. We're still collecting individual numbers per sample. But these are numbers that correlate to how the interaction is using the device's resources. And if you think about performance, you can think of it as this game of resource usage. It's making something faster is about making the resource usage, lowering the resource usage, optimizing it, scheduling it better, not contending for resources. And it's all about these primal things on device. And it's these things that make up a computer, right? It's the CPU, it's the memory, it's the disk, it's the network. And it's all about how we use them within our interactions. And when I say this, by the way, I'm not talking about disk usage, as in how much space we're using. I'm talking about how we're reading and writing to disk, because there's these disk queues, and there's a lot of latency involved there. And this is by far not an exhaustive list, but these are the first 4 things we always look at. So how do we get these things on an actual device? Well, the CPU one is fairly easy. There is a metric that the kernel collects for every application called the CPU time. How many seconds were your threads actually running on a core? And you can get to that from native code via a standard library call called getRUsage. The 3 in parentheses indicates it's a standard C library call. And you can Google this and you can figure out how to call it. And it will tell you the how much time you spend in the kernel, how much time you spend in user space overall for your process, or per thread. Second one is memory. Normally, for Android, that means Java heap memory, and because that's where you introduce garbage collection, and that's where most of the latency would come from. And one way to get to that is Android OS debug. There's a lot of interesting markers in there and telemetry that the VM can collect for you. The thing in question here is start allocation tracking and stop allocation tracking. So you start the interaction, you start allocation tracking, you stop it at the end, and then you can ask this class how many objects were allocated, well, what was their size. It can't give you details like classes and heap snapshots and stuff like that, but it's enough to know the count. And remember, like we're still talking numbers only. There's a lot you can do with numbers. Disk I/O is harder. You have to manually instrument it basically within your app. So in your disk caches, you have to manually instrument when you open a file, write, read, close, etc. But there is another type of disk I/O that the kernel can track for you, and that's called major faults. The way code is executed on Android, it's not the process is not actually reading it via the normal calls. Like it's not opening your APK and reading from it. The kernel is giving you these pages of disk inside of your memory space, and that's called a major fault, and you can get that from get_r_usage. Each major fault corresponds to 4K of memory being read from disk. And lastly, network I/O. Again, you have to do this manually, but the good news is that most of the network libraries out there already have some type of listener for this type of telemetry. And there's also a separate class of things I like to call pseudo resources. These are mixes from the primitive resources that come up often enough that they're useful to track on their own. Class loads is a common one, especially for startup, which is the number of classes you're attempting to load. That's you can instrument that by installing your own class loader. That's fairly easy to track. You're just incrementing a number every time you try to load a class. Concurrent network operations, especially if your interaction is network bound, that is really useful to track, and you really want to keep that number tight and controlled. And of course, any other application-specific things, depending on what your interaction is. Okay, so we have these resources. What do they look like during our regression? Well, class loads look pretty stable. So this is between P45 and P94 on the y-axis. And the top percentile is always a lot more wavy, and because there are just very few samples there. And you can see there's kind of something going on, but we actually investigated this, and there is actually no change in the number of class loads. CPU time. Okay, so that looks very, very flat. And we actually investigated it in great detail, and there was no change across any percentile in the amount of CPU time that we use. Okay, now we're getting a bit scared. Disk I/O. Again, there's nothing in the high percentiles that spiked. So remember, our regression was primarily in the P70 and above, but all of these look the same over time. Like, they all change the same way. They all look like the same interaction and resource usage. Okay, now what? Well, if you think about it, what this is really telling us, and by the way, I omitted a few charts here. We looked at all the resources we could get our hands on. Like, there was nothing that moved. If you think about this, what this is saying is that the interaction is using the same resources, just more slowly, somehow. And this is really hard to make actionable, right? Like, it's really hard to determine how this is possible. So we need even more telemetry. And at this point, it's useful to start talking about traces. A trace, the way to think about it, is basically a time slice. From point A to point B, tell me everything that happened in my application. So if you've ever used ABSYSTRACE, that's basically it. But ABSYSTRACE is for the entire device. We're only interested in things within our application, the things we can control. And another way to think about traces is basically as even more counters, even finer range. So instead of collecting these resource usage counters over the span of your entire interaction, you can collect them periodically within your trace, and you can then plot them. You can get things like thread level granularity for these counters. You can get method level granularity within your trace. But, and this is the hardest part, you still have to obey those same constraints we had at the beginning, namely the data usage one. Traces are really easy to make very, very large. It's really easy to make an inefficient system that collects multi-megabyte traces. That is definitely not what you want. So given all of these constraints, we have an internal tool called Loom. And what Loom does is, for any interaction, we can set a sampling rate that we want, a trace collected from it. And the traces we get back look a little something like this. So we have stack traces on top, and then we have markers on the bottom. And this is a single thread, by the way. This is only one thread. I've omitted all the names because they're not really relevant. But what's really interesting is that you get these different shapes of stack traces, right? Like you can kind of see the icicles look a little bit different. And so you can take these icicles and you can visually split them into separate groups. And you can see that this interaction has multiple phases. So now even over each one of these phases, you can start aggregating these counters. And then maybe you start narrowing down like which part of the interaction regressed. Was it the first part, the second part, the fifth part? And you can start seeing like how do these counters and resource usage correlate with individual methods in your stack traces. Of course, this is really hard to do manually. This is really hard to do by looking at a single trace, and you want aggregation over it. And that is a separate talk on its own. So back to our regression. Okay, so we have traces. What do they tell us? Fortunately, we couldn't use Loom. So it turns out there is a specific case of interactions where it's really hard to start a trace at that point in time. And this regression fell into one of these places. And basically, the traces that we got back from Loom were saying that everything was fine with the world. Everything looked the same. All the aggregations we pulled out of it, stack traces or not, everything looked the same. And what this is really a lesson in that even if you have amazing tools, you shouldn't trust them all that much. You should always have a sort of a simpler fallback plan. And going back to first principles and thinking about how is this possible, what behavior on the device can explain these numbers that I'm getting back from it, is a really invaluable skill. So what was the regression? Well, it was lock contention. There was a global lock that was introduced in this version of the app, and this lock was being accessed by 5 or 6 threads. But that's really not enough to explain the 10 or 15% jump. And so we started digging, and we found there was priority inversion. The lock was first taken by a background priority thread, which is the lowest priority you get on Android. And that priority is shared with all other background processes. So your background priority threads within your app are sharing the same 5% of CPU time with everyone else on the device. And so that lock was first taken by that thread, and then the main thread started waiting for it. And if you think about it, it's the same amount of CPU time that's being spent. It's just being spread out through time, which is exactly what we saw in our resource numbers. The CPU time, as in time that we were running, was the same. We're just running a lot less often. But we now know how to catch these. If we collect the CPU time per thread priority, and we aggregate per priority, we can see CPU time shifting from the high priority threads to the low priority threads. And that is a sign of a priority inversion. So for us looking forward, we basically have the opposite problem now. We have this really fine-grained data, and it's really hard to get a lot of signal out of it. So we're looking a lot at automation, automatically correlating resource usage to functions, to specific spans, to phases. Anomaly detection we already have, but it's even harder to make that on a per method basis. And automatically detecting those interesting filters, those interesting combinations of countries, device year classes, and maybe network conditions that are indicative of a regression. So in summary, I want to leave you with this. If you're starting to look at performance on end-user devices, it's useful to start thinking about the average as something you may want to track. Don't trust it as an absolute number. No one is really experiencing that number. but it is a useful single number to track and monitor over time. Learn to look at percentiles, histograms, distributions, and learn to love them. They will become your life. You need to get a sense of how these histograms move with regressions, how they move with improvements, and it's a really invaluable skill. Device year class is a great abstraction. You saw the lines, how clearly distinct they were with the device performance. It's very useful to look at it and to look at the device mix under this lens. And lastly, resource usage counters. There are probably the simplest thing you can do that has the most bang for buck, while still keeping your data usage very, very low. And when all else fails, think about building traces. Think about getting a lot of detail from your app about what it was actually running, what methods it was running, what sub-interactions there were within your overall interaction. That's all I have. My name is Delian. I'll be at the Facebook and Instagram booth if you want to chat. Thank you.